Good afternoon, ladies and gentlemen. It is a great pleasure for me to welcome here Martin Stýblo from the Simone Research Group. Today's talk will be a little bit more applied than usually, but I think it will be interesting for all of us. Martin studied at the Czech Technical University at the Faculty of Nuclear Sciences and Physical Engineering, and since then I think he is
single employer, single career, yes,
involved in the Simone Research Group company. Actually, it is a pleasure for me to welcome him here, also because we studied together at the high school together with Martin Kružík, so all three of us. So it is nice to have Martin Stýblo here for the talk, and we are looking forward to your presentation. And please
thank you, Peter, for very kind introduction. So once again, ladies and gentlemen, good afternoon. My talk will be really less theoretical, more applied, and the aim of today's presentation is to share some basic insights into industrial pipeline simulation, about the equations, particularities, method used, and I'd like to end with the outlook, what's actually live in the development research directions that the industry is trying to test and heading for. Yep. So as already said during the speaker's introduction, I was born in 1970, graduated from Czech Tech Faculty of Nuclear Engineering, Nuclear Science and Physical Engineering, applied mathematics, and since then I'm actually dedicated to single career within Simone Research Group, taking care about one of the say industrial simulator packages. My own background is more PDE and numerical mathematics than the rest of the field, and the duties cover the taking care about the simulator core. That means the governing equation and their discretization, handling with gas physical properties. It's a gas simulator package, so I will concentrate on the gas side of the industry. Also bringing the equipment models inside, because they constitute a big part of the pipeline modeling. And since last 2-3 years, I'm quite heavily included in one of applications, that's the calorific value tracking over transmission and distribution grids. This is linked with the renewable gases like biomethane, eventually hydrogen being injected into traditional natural gas grids. This leads to calorific value change. Metering on the customer interface is always volumetric, so there is a need for recalculating the metered volumes into the traded energy. Good for us, because the computational reconstruction of gas calorific value is probably the most reasonable option from the possibilities we have. Last few years, I got the honor to become a member of PSIG Board of Directors. That's the top industrial conference gathering software vendors, pipeline simulation engineers from around the globe, with the center of gravity in the New World. But the main point, it's probably the only independent forum for this. The other conferences are usually like vendors, user group meetings. So the pipeline simulation as a topic is about calculating what's happening in pipelines, transporting primarily hydrocarbons as a source of energy. That was the primary motivation since human civilization is using hydrocarbon fuels for last 1.5 centuries, say. So that's the traditional part. It includes gas, liquids like crude oils or products, eventually two and more phase flows. This is a very particular part of pipeline simulation, and honestly, it's so specialized field that we will slightly leave it aside, though it's fascinating. We will concentrate on gas in my talk because my background comes from gas simulator package. I will try to tackle the important links to liquid side sometimes. Pipelines do carry also water, wastewater, water for heating, steam for heating, any fluids in industrial plants. We will leave this big branch aside. Pipelines can carry, say, non-traditional gases like hydrogen. Nowadays, it's not fuel. Fuel is bad. It's hydrocarbon, and these are bloody emission-causing fuels. So hydrocarbon is an energy carrier, and CO2 is here, waiting to be transported in our beautiful carbon-free future. On the other side, staying low and humble. The share of energy that is currently transported or distributed by pipelines in form of the traditional hydrocarbon fuels is so huge that those will stay with us for quite a long time. At least at the moment, there is no technically feasible way to supplement the funny behavior of renewable electricity generation. The only viable way is to use gas-fired power stations to shave the peaks and the bottoms of renewable electricity. Pipelines are also used to distribute gas along areas nationwide, citywide, local networks. And again, 100% electrification is deemed to be too costly in many regions. So let's stick with the hydrocarbons in pipelines, mainly with hydrocarbon-based gases inside of a pipe. For what we need to simulate what's happening inside pipeline networks. Quite naturally, to design the pipelines or to plan their extensions, eventually plan their retirement. We also need to support daily pipeline operation. The pipeline operators do carry some kind of contractual capacities they are obliged to handle for the shippers moving commodity using their services. And there are some short-term, like daily cycle nominations within the already signed capacity contracts. So they need to verify, can we handle the next coming load under the current conditions, taking into account equipment outages, maintenance work, etc. How to operate the system in terms of minimizing fuel, gas, or compressor energy consumption? Quite natural question. What ifs, decision-making support, how to handle non-standard situations before they happen, make some emergency plans, or react to some non-typical situations. this way of thinking can grow into, say, sort of risk analysis and mitigation or reliability studies. Transmission pipeline has to handle possibility that not all compressor units are available and be ready to assess the impact for the capacity, etc. Composition tracking in case of gas pipelines, motivation was already mentioned. Another thing, off-spec gas can enter the pipeline. It's good to know when it comes. Can we handle it via some activity happening across the system if we have some degree of freedom? Liquid pipelines do often operate in batch mode. They are sending batches of particular liquid, especially if the pipeline is transporting products. They run a batch of gasoline, they run batch of diesel, they run batch of kerosene, jet fuel, and they have to handle when the batch arrives, how the interface zone is to be estimated, because that's something to be wasted, because you cannot spoil the prescribed purity limits of the products, etc. Of course, we may use the models for leak detection and localization in the nature of having flammable and environmentally not polite stuff being transported is quite important thing. And as already mentioned, in gas world, calorific value tracking is of growing importance. The share of the outlooks of usage are even wider that we can imagine, and I can tell you that the users could be pretty clever to think about nice problems. There is a nice buzzword you might see in the corporate lingo, digital twin. Everybody wants to sell digital twins. That's the model. I don't feel it's a right way, and my diligent competitors, the technical people, we are always laughing because it's a buzzword. You need the model, and it doesn't really depend whether it looks exactly like SCADA system interface. That would be the ultimate digital twin. But is this what I always want? I need a model. I have a wide context of using that model. So let's talk about modeling and forget the buzzwords. Some little introduction to history of the industry and some context. The stuff being transported by pipelines, I mean fuel things. Town gas era started mid 19th century with a coal gas called town gas produced locally in a city gas works, and then the network to distribute the gas emerged. So since, say, the end of 19th century, we can see first flow equation in terms of how to calculate a pressure drop against flow rate over a pipeline segment. Crude oils and liquid products started to be transported by rail in barrels or in railway tracks. There is always a milestone in the history of our industry being emphasized, and that's the World War II project Pluto pipeline under the ocean, because it was starting tremendous effort to design it, and most probably that was one of the triggering events in the history. It's true that during 20th century, we see pipelines transporting crudes, pipelines transporting natural gas on long distance, transmission pipelines. So since during the 20th century, pipelines are all around the continents, then they go undersea from production platforms on seabed to onshore receiving terminals. So the plethora of pipelines is still growing. Pipeline simulation, looking for digital way of modeling, is to start about end of 60s, thanks to the availability of relatively cheap computational power in terms of mini computers. There were some attempts to play with electrical analogs, but due to inherent non-linearity of the equations, mainly for compressible gas, it was smoothly going away for use of numerical models and computers. The heart of our job is something that we can condense into another buzzword, less stupid. It's a fluid mechanics on a graph, which makes quite a sense. You can easily view the network or grid as a graph, where the edges are pipelegs, valves, or some pieces of equipment like compressors, pumps, regulators. And the nodes are just plainly connecting two pipelegs, making a junction. And there might, not all nodes might be the places when the fluid can enter or leave the network. The governing equations then on each edge of the graph, we view the flow as a one-dimensional approximation. So let's stay a little while with the equations. This is not a rocket science. Imagine a pipe with cross-section denoted here by A, and we have a mass balance in terms of continuity equations. All the quantities are assumed to be like cross-sectional averaged values of density. Mass flux is A rho V then, etc. So we have a mass balance in terms of continuity equation. We can derive the momentum balance in a form that at least the three terms from left look exactly like a quasi 1D Euler equations on a nozzle with a cross-section of A. The friction forces we handle, including all the turbulence modeling, are mimicked by Darcy-Weisbach's law. So a magic friction coefficient does all the magic behind. There might be non-negligible potential energy thanks to density, quite for orientation. As an example, natural gas in 5 megapascal might have like 30-35 kilograms per cubic meter operating density. Crude oils might be 600-800 kilograms per cubic meter. CO2 in dense phase is something similar and then yet compressible. So quite naturally, we should take the elevation sometimes into account. And of course, the energy balance equation is here. Again, from left, the I'm fighting with mouse, but three terms from left do resemble the quasi 1D Euler equations. But generally speaking, we might have some funny term with cross-section, and some models do take into account that the cross-section of pipe is time-dependent, thanks to pressure acting on the wall of the steel pipe. It might be interesting for those heavy and less compressible materials like crude oils or products. And to complete the energy balance, there is a heat flux between the fluid inside of the pipe wall and some I would say, undisturbed outer soil or outer environment temperature that is a bit far from the pipeline. So that's it. If we take away the friction terms and the heat exchange terms, it's a nice hyperbolic system. Three characteristics: velocity plus minus speed part of the equation set. First thing is the magic of turbulence and laminar flow that is hidden in Darcy-Weisbach friction factor denoted here by lambda. So everybody loves Moody chart saying that friction factor is a function of Reynolds number and dimensionless ratio of wall roughness against internal pipe diameter. Everybody knows that 2000 of Reynolds number are the magic. That's true for rounded pipe. And actually, we might have the fully laminar flow in Hagen-Poiseuille equation. Then we have a known transition zone when things go wild because turbulence kicks in, but we don't care. We think that lambda is hiding this for us. And generally the friction factor jumps up dramatically. And since we are far from the transition range with some another magic 4000 value of Reynolds number, then the traditional turbulent part of the Moody chart kicks in, and we are more happy because then we see typical behavior. This area is also sort of transition between like whether the flow is still with some influence of the boundary effects from roughness, and this area is like fully turbulent flow. One famous is the Lipporadze limit for big Reynolds numbers. Another famous area is the smooth pipe law here. Where we are here, it depends with the media. Crude oils might heavily play here, so sort of smooth transition modeling is crucial for them. Gas, however, quite easily comes over the magic transition 4000 value of Reynolds number, and we can be happy. And we just need to do some conservative jump back to laminar law if we ever need it. But quite easily, if you look to natural gas pipeline, you are almost always somewhere behind the transition range. So that's it. That's the rocket science about turbulence. Another important thing, everybody knows that the set of equations has to be closed by equation of state, constitutive relation between pressure, density, and temperature. For gas, we tend to use equation of state expressed with compressibility factor. And it's true that in our area of interest, gases are no more ideal. So Z is not equal fixed one. Z is something that is usually by the most popular and used equations of state is some expansion in terms of density or molar density, temperature, and composition. We also have to play with some another thermodynamical properties. As a consumer of thermodynamics, give me a Cp of ideal gas, and the rest can be derived from the equation of state. There are typical equations of state intended for pipeline gas quality region. There are equation of state developed for handling of phase equilibria. There are simple formula for handling low pressure regions. Usually the packages offer selection of many possibilities, and it's up to the user to take the reasonable equation of state. And in fact, this choice is not negligible. Of course, everything comes with some trade-offs, performance, accuracy. And one of the pilgrim fathers of the industry, Jerry Modisette, said somewhere early that most of the simulators spend most of their CPU time battling the equation of state, and it's true. Definitely we need viscosity. There are empirical formulae used either for liquids or for gases, typical for natural gas. Since 60s, we have some nice simple formula, but you can now find say sound composition based approximations that seems to work quite nicely, and we might use them. Eventually, we may ask about heat conductivity. Honestly, it might be of interest for like crude oils, for liquids. For gas, the interface layer, the heat transfer, the wall heat transfer coefficient is high enough to be neglected in the chain of heat transfer effects. The heat transfer, if it comes into game, is also something particular we have to tackle with. Why? If you compress the gas, just to have some idea, transmission pipeline might roughly run. If it is onshore pipeline, it might run roughly 75 bar maximum operating pressure, and the compressors will run for, say, somehow 50 something bar to 70 through the compressors, and then the next pipeline leg, which is like 100 miles, 150 kilometers, say roughly, and you will lose those 20 bars roughly along line thanks to friction. So it's another place and time to compress the gas again closely to the operating pressure and then back. So you have the saw teeth diagram along the pipeline. And after compression, the gas is heated pretty much. On the other hand, nobody wants to see too much degrees centigrade entering a pipeline that is coated by some bitumen corrosion insulation, because if this melts, you are in big trouble. If you destroy that, you are going to dig 20 miles of pipeline downstream compressor stations. So we have to play with non-trivial temperature of gas, especially in transmission. The same might be a question of crude oils, especially or in production gathering lines. The crude oils from wells might be warm enough. So if there is some non-trivial gameplay between surrounding soil and the media temperature, heat exchange has to be considered. And what we know that the idea just to get an overall heat transfer coefficient between inner wall and the outer place where the soil temperature is placed. It's nice, but definitely not adequate for transients because there is a lot of capacity in the surrounding soil. If you have onshore pipeline covered by soil, typically 1 meter above top line is the cover when building the pipeline. So you have a nice area that is either cold or preheated and has a quite substantial capacity inside. And first observation is that if you shut down the compressors in one place, so you lose some pressure and you lose the high temperature. But thanks to having preheated the soil along these 150 kilometers, the next station downstream will notice some change within a week. So we need to play with this capacity. And most of these simulators are using a sort of cylindrical shells around the pipeline with estimated properties nobody knows, like density, Cp, and heat conductivity. And typically the model is to be solved along the pipeline model. So as a funny thing, we might easily have a higher number of degrees of freedom outside of the pile than on the graph of the pipeline network we are playing with. But that's the physics. Some simulators try to use some simplified analogs, avoiding this computational burden possible, but simply you cannot ignore. Once you need a temperature, you'll probably need to play this because the long time constant here, that's like days. And our window of interest is 1 day. So typically all the time of interest, the game is being played here. So the models have to play with this. Equations to be continued. What we do with the equations? You saw that the idea to write them down resemble the conservative form of equations. Nice, beautiful. But there is one technical issue. Density is something that you don't measure directly on a field in the pipeline. You can see pressure meters, flow meters, you can see temperatures. Sometimes you might know about like supplied fluid composition. So most simulators tend to rewrite the equations into something that we might call primitive variables. Pressure, mass flow, that's quite nice. A times rho times V make sense. But the pressure and temperature are much better to handle directly because you need to face boundary conditions, equipment set points. You need to face measurements. The way to do that usually is introducing a enthalpy, or in fact total enthalpy, including potential energy, and introduce it into the energy equation. And then there are some nice thermodynamical ways to say that the enthalpy derivatives can be translated with Cp to temperature and pressure derivatives. So that's the way how most of the software handles the equations. There are some other possible simplifications, fixing pipe walls, saying A is constant. Some people claim it's bad because it follows wave propagation speed of sound. On the other hand, it depends on the application. I have less issue, and what we do with our system, we keep for gas pipeline the cross section fixed, not depending on pressure. For compressible liquids, you are typically in a subsonic region. You might face sonic effects like throttling in nozzles or ruptures venting the pipeline, but these can be somehow handled locally, and the equations or the fluid in pipes tends to be slow, and there is some chance to get rid of some terms in the equations if you say, okay, I will deal with subsonic flow only. As a little example, this is how the job looks almost in Simone, in our system. Here we introduce pressure, so there might be some funny coefficients. Here we introduced the subsonic flow assumption, getting rid of some ugly term, and we have a very nice base of equations, looking for some staggered grid and finite volume approach. Very nice thing. Energy equation, as indicated, playing with energy enthalpy, you finally get something like a derivative of T times rho times Cp. There is some funny pressure term, not avoidable. There is a term that can be linked with Joule-Thomson coefficient of the fluid, and Joule-Thomson effect is really visible on gas lines. If you run a heavily loaded transmission pipeline, you can feel the little subcooling of the gas because pressure is going down thanks to friction losses, and thanks to Joule-Thomson effect, the equilibrium tends to, and if you settle things to stabilize, you can see that the gas at the downstream end of long pipeline might be slightly subcooled, few degrees of centigrade against the soil surrounding temperature. And there is the heat exchange terms, which is supposed to be in transient modeling produced by the interface with the heat flux model. Numerical methods we use to battle those equations, they do, of course, utilize the hyperbolic nature of the equation system. On the other hand, we don't need like high resolution schemes because we are not chasing shock waves, definitely. We are, in fact, in chance to be interested in contact discontinuities, but batch tracking, composition tracking. But not surprisingly, a more effective way is to introduce some moving grid for the quality nodes rather than to fight with excessive numerical dissipation of any fixed grid scheme. We don't like to play with high resolution schemes because their computational stencil is wide, and we would like to benefit a finite graph-like approach to easily handle the network topology. So the typical methods used inside industrial simulators, still sometimes method of characteristics or potentially some other way to do upwinding and either explicit time stepping, eventually semi-discrete time stepping, semi-discrete formulation is used, but with a plain explicit scheme, there is no escape from Courant-Friedrichs-Levy condition. And these simulators doing this can do incredibly well in terms of catching water hammer effects and stuff like that, but they are small. So most of people tend to do something different, and quite popular approach is usually called box scheme, because we don't play with shockwaves. We don't need that too much upwinding and this kind of approach. We, as simply as possible, take like some surrounding knots in space and in one and next time level and integrate over the time spatial box. That's why it's called box method. My diligent colleagues remember that it's based with some French guys doing river flow modeling. In fact, our Pilgrim Fathers did also in 70s something like for a river modeling. And what they do is something that could be called box approach, because we integrate as it comes, not looking too much about characteristics. Another probably nice term would be staggered grid. If you say that some quantities are in nodes, like pressures, then it's quite natural to assign flow rates to mid of the biplex. That's quite a nice idea that straightforwardly leads to something like finite volume approach to the discretized things. So quite often the things can be viewed in a semi-discrete way, that all the coefficients given with playing with the equations, integrating them over, say, pipelec, then you have some big but sparse matrix A, and usually because we would like to have unconditionally stable schemes, so usually sort of semi-implicit theta scheming is done to march in time. Theta slightly above 0.5 to get rid of even odd Crampton-Holson-like oscillation is used, or we use fully implicit time stepping. Some simulators tend to use some clever way, which could be viewed as a Richardson extrapolation, if you want, or not Runge-Kutta. It's some way two-step approach to get a second order in time, but with a single evaluation of the Jacobian matrix A. So A contains the, say, left-hand side equation coefficients and scheme introduced things, and the right-hand side vector is about boundary conditions, flows in, flows out, friction terms, energy exchange terms. For the scheme, we do evaluate, so there is a linearization based on we do evaluate in the starting time level, and hopefully implicitly solve for the next time level. A is big, but sparse, or eventually with some nice structural properties that can be utilized. Our Pilgrim Fathers introduced because they battled in 70s with many computers available, and there is a lot of legacy code in the industry, by the way. Everybody is battling old Fortran kernels fed by text files that resemble punch card files. And so there might be some way to structure things that you have a branches with in staggered scheme, tridiagonal metrics, and you might have some nice symmetric metrics to handle pressures or densities in the crossroads connecting the junctions, which is memory saving and translating things into symmetric small sparse problem. But generally advances in sparse linear algebra are big. So many commercial softwares use some commercial sparse solver, and they are pretty happy. The dimension is in the order of 10 to the 5 and more. 100,000 nodes is quite to see, not often, but 10,000, thousands of nodes, it's a common thing. And I'm gradually marching till the end. So equipment models is a big part of our job. Basic equipment are compressors, eventually pumps for liquids to overcome the pressure loss along long distance transport. Still, transporting energy by pipeline is a relatively cheap thing. Electric wires are not perfect either, so still be happy for pipelines we have. Old reciprocating compressors, this is in fact a displacement-based device that has the throws and pistons pumping. So you start from the PV chart, but you probably need to like integrate the PV chart and translate it into something better. The something better is usually adiabatic head for gas and intake volumetric flow. For pump, it would be head, elevation head, or pressure increase and suction flow. Because centrifugal compressor is a device that translates the rotation of the impeller via famous Euler equation of Blake into increase of enthalpy of the fluid that is rotated through. So with some little work here, our natural field to play is adiabatic head, which is isentropic enthalpy difference, and intake volumetric flow rate. And this is the area when the centrifugal compressors are drawn their envelope. And the compressor people can tell you that adiabatic head versus intake volumetric flow is the perfect case because it's almost and reasonably technically invariant to gas composition, gas gravity. So it's a fixed picture you can play with. There is some thermodynamic model inside to be played with. Most probably why we need to play things up to that detail to handle a situation that you are out of driving power, that you are limited by drive power, and sorry, you cannot, you are doing less than expected. The job of equipment modeling is then, in fact, to be robust against all crazy chances the network can play around, and to always give some reasonable answer from the equipment towards the network. Another equipments are for gas lines, regulators, which do throttle the gas. Typically, you go down from transmission line to distribution, which is operated on lower pressure level. So you need to safely interface them. You have a regulator that regulates a flow rate in a way not to exceed the outlet pressure, or it's directly flow controlled. So basically, it's a nozzle that throttles the flow. Sometimes you might want to go into detail, and you have a valve sizing equation that plays with the sonic effects inside of the geometry. And of course, there is some thermodynamic process. It's a almost isoenthalpic throttling. So you have Joule-Thomson cooling or a little heating with hydrogen. And if you are cooling enough, natural gas roughly goes half a degree centigrade per 1 bar pressure step down. You don't want to have freezing things. So you might have to preheat the gas. So again, there is some place for the process modeling inside. Or you might have a check valve that goes this way, but not up. And everybody in the industry tells you this is the most ugly of them all, because it has like better gain along, and everybody tells if you don't need a check valve in your network scheme, don't draw it. That's true. And in fact, the game played with equipment modeling is to match the equipment model, which is, by the way, almost always described as a static relation. There is some inherent dynamics going on, but who cares? It's usually faster than the time constants of the gas network around, though not surprisingly, liquid simulators might have to give you even like PLC logic and PID regulators to be programmed. That's true, because if you have transient in a liquid pipeline, the transient are quick and rough water hammer effect. So you might want to, but for gas, we typically treat things as a static relation, and we need to, what's happening is you need to match the equipment edge in the network graph with the surrounding network upstream and downstream. So typically you derive something that is called network load line or resistance line or something like that. And you derive it from the like step equations. And there are quite natural relations, like if you pump more, your inlet pressure goes down and your discharge pressure goes up. If you pump more, you can somehow translate with some linearization effects locally at the time being. If you pump more, you need more adiabatic head. But then you can translate the network gain at the moment of the step with the equipment model and match, solve for the equipment model and go on. That's why historically the method of characteristics was popular, because it quite nicely and naturally gives you those relations easily. Further simplifications. We can throw away temperature, saying it's fixed or assumed. The question is if this is adequate. It's nice to have like pressures, mass flow rates model, but still the question is if it is adequate or not. I would say not adequate for transmission line with compression, pretty adequate for distribution system that is not heavily loaded, and you know that the gas inside tends to settle in reasonable equilibrium with the soil temperature. But you might still not want to forget the temperature, because summer, winter, different temperature, different line pack under the same pressure. So it still might require some attention. Another thing is steady state calculations might be easy. You drop time. So you drop time derivatives, and there are basically two approaches. One approach is really start from steady formulation. The other approach is artificial time marching. Both are used. Both have their pros and cons. In fact, flow equations from the old century, these were those. If you say, I have a compressible gas with a pipe segment of length L, diameter D, assume temperature T, assume compressibility Z with those heads, that's the assumed fixed things. I have a mass flow M, and I integrate it over because it's compressible. I get this famous formula. The difference of P square is something times friction factor times the M square, but oriented M square. By the way, for people playing with this, this is the ugly term for an linearization. Then you can translate things in sort of like a big non-linear set of equations for nodal pressures. Some solvers do. And in fact, if you throw away temperature and it's adequate for distribution grids, why not do that for this city grid modeling? Because then you might be happy to have 250,000 degrees of freedom in terms of nodal pressures, rather than 2 times bigger for time stabilization, because roughly you have 2 times bigger for nodal pressures and element flows. On the other hand, those direct formulations tend to spend a lot of effort to be robust against like ill-based problem formulation, not enough boundary conditions, stuff like that. So I met people saying we throw away a steady approach and use artificial time marching because it's easy and even more natural to diagnose this kind of problems. I could agree. We do use time marching. Okay, real-time models. That's something that makes sense. If you want to support decision making on a real pipeline, you need to estimate the state of the model right now to be able to like run look-ahead simulation. What happens if we do nothing and meet tomorrow's nominations? Will we survive or not? Starts maybe some what-if games and stuff like that. So basically, the typical issue is that the problem dimension is big, but the number of measurements available on the system is much, much smaller. So some sort of state estimation technique is definitely used. What the industry usually tends to use is sort of engineering shortcuts. Most typically, it's sort of that some people can even, maybe with some inspiration, statistic called the maximum likelihood state estimation. In a very short, almost vulgar way, I would say we need to fit to our measured values in some least square sense, but we know that we are constrained by like step equations for the transient model. So that's the way how this is expressed. History, the first thing was called the equal fraction method, saying in a node I have available pressure reading. I will say that I will make like a Newton type boundary condition. Metered Q minus modeled Q divided by accuracy of flow measurement is equal measured pressure minus calculated pressure divided by some accuracy of pressure reading. It's nice, it really works to move you towards measurement, but on the extent of having some parasitic boundary flows, which is not nice completely. So it's a robust, easy, fast, but most vendors did shift a bit from that, aiming to have really a more consistent state without parasitic boundary flows in place you don't want to see them. I even saw a fully motivated approach like being tested, like Monte Carlo Kalman filter approach, but it's too small, too slow for us. We don't need, because we are not playing with things like shock waves, and our dimensions of the problems are not that big. We are running on humble computers. We don't need parallel power too much. On the other hand, we need our real-time models to update in a cycle step that is like 1 minute, 3 minutes. So you want to be fast reasonably enough. Most of the software uses either some kind of calibration tools, or even within the real-time model, some slow calibration, like of roughness or pipe efficiency. to improve the estimated network model state. Once you have it, you can usually deliver the real-time system as a state estimator and automated look ahead. Eventually, if you have a state estimator, you may start looking for leak detection. Typically, a bit different state estimator is used for leak detection. The basic idea, in fact, the leak detection is a tricky thing. You might have a number of approaches. External ones, like sensing the fluid outside. Internal ones, using the field measurements to retrieve information what happened. And a typical way is RTTM, real-time transient model-based leak detection, which is in fact based very quickly running the real-time model to estimate the packing rate, especially if your fluid is compressible. The packing rate is of a big interest. You measure the flow balance, the outer flow balance, flow in, flow out. You might know it. You use the real-time model to get the estimate of packing rate. So then the difference, flow balance, like metered flow balance minus packing rate, it's the observable balance. If it is small, if it is zero, things are okay. If it is big enough, we have an offtake we don't know about. So we most likely have a leak. Typically, then the real-time for pressure, like outer flows, and you might play the balance game. So basically, main thing is that from the observable balance signal, something is retrieved. In terms of hypothesis testing, like was the jump or change of observable balance significant enough that cannot be explained by some threshold from measurement accuracies? If so, we probably have a leak. And that's a true game. And once you have a leak size estimate, you might aim to localize it. There are some approaches called hydraulic gradient intersection. If you have a pipeline going from A to B, and you know that along the pipeline is some estimated leak size, especially for located people do that they draw gradients adding the leak size in the downstream end, and when the hydraulic gradient cross, there is an estimated leak size. Things with gas networks make things complicated because of compressibility. You may do trial and seek, try to test, try to position the estimated leak and try whether you fit to pressure readings, but that's all. Optimization, it's our holy grail of the industry. The hint how to operate, especially those energy consuming things like compressor or pumps, in order to transport what we need to transport and consume as less energy to run the compressors or pumps as needed. That's the goal. So the objective function is fuel gas or simply the input energy. Control variables are usually flows, eventually pressure set points of those active devices. And a little disaster comes if you want to play with discrete variables like number of units needed. This is a bloody combinatorically difficult issue. So some sort of heuristic games is usually played. Our constraints are in fact the network model equations. And because what's happening is interconnected with the network behavior. And of course, typically we have some inequalities in terms, we would like to save our compression work, but please keep the very downstream at least on 50 bar, because it's a contractual value. The cheapest way is to forget things, and for a while it will stay. But we need those kinds of constraints. Question is, what's the time horizon, or what state of network or development of network to optimize? Steady state optimizers are useful for liquid pipelines because transients are quick, and those lines are really operated jumping from steady state to another steady state. So that makes sense. For gas, this makes sense for long transmission lines. They still play some game, but if it is around over the big trunk load, the steady state approach still is technically feasible. Or, and this is a true holy grail for gas optimization, transient. How to do things to survive next gas day along load given, constraints given, to move what we need to move and stay within our constraints and do it as cheap as possible. So quite naturally, there is always a trade-off between how detailed we model the physics and how complicated the whole problem is. Typically, we can say that steady state optimizers with a device description up to very detailed are something like industrial standard. There are transient optimizers. In most cases, they are linked with some simplification, either network model or compression model, especially in academic research. It's using a simplified network and device modeling, almost black box modeling. But the game is to play with the solvers. So why not? Methods. The packages mostly still use gradient-based methods with all their nice properties and bad properties. You can be easily trapped into some local funny extrema that is not nice, not physically correct. There was, for the discrete things like number of units, either some heuristic was used, or there were attempts to use like linear programming or piecemeal linear programming in mixed way with integer variables, and the results, sorry to say, are often mixed. So it's still an open place. So I'm gradually going down to our end with some new ideas. Simulation itself is mainly now tackling with new media. Hydrogen is a gas. It's a funny gas, but still gas. CO2, it's another story. For long, this CO2 is ugly gas by its behavior. Anthropogenic CO2, which is to be from the carbon capture and storage chain. So it's a CO2 being captured from like fumes. It's impure. And there is a huge impact on impurities on the physical properties. And the point is that the idea is to gather things, and then gas phase for gathering system could be technically feasible. But if you would like to, the inevitable CO2 emissions, and sorry to say, Greta, we need the bloody crude oil refineries to have plastics and stuff like, and they'll still need that. And there are some industries we still will need. So we would need to capture and probably store in the depleted fields, for example. So the long distance transport is assumed to be in the dense phase region. And then you have a ugly stuff like density close to crude oils and also compressible. So that's something. With some care, you can play with a single phase simulator, but with some care. You have to circumvent the two-phase area, which, thanks to impurities, is moving. Optimization, still active field. We can see like a traditional approach oriented to using new capabilities of mathematical programming, new solvers. Mostly like tested with simplified physical state models. Quite recently, there is a number of nice papers about brute force approach, like genetic algorithms and a farm of, it was a steady state optimizer, like big transmission line planning, week ahead, next day ahead. Basically a regime suggestion for the control room. And they decided to play with genetic tools and a farm of steady state solvers. So like brute force approach and very coarse granularity parallelization, but probably it's promising. Maybe it's more promising that nice, clever, closed package approach, because then, sorry, we are limited. This nicely opens things. And those genetic algorithms might be promising things to tackle with all those bloody combinatorics. There are people talking about LLMs emerging. Big question mark. My main issue is I can imagine for the genetic gameplay that steady state solver, even for complex transmission, can be fast enough and can be like a single atom brute force paralyzed to help the population to grow and learn. Why not? But I'm not sure how to effectively train a large language model with all our capabilities. Sorry. But we'll see. Another thing is uncertainty in modeling or optimization. Motivation is clear. Synergy of gas and electricity systems, and you have a lot of uncertainty with renewable electricity generation. So quite natural, people tend to include in their considerations tools to mimic the uncertainty and get ready for this. Gas pipeline has a line pack. You don't have too much line pack with electricity. Still, batteries and stuff like this are orders of magnitude away from what we would like to need for short-term or seasonal storage. Gas offers short-term storage in line pack and a seasonal storage. Another field that might be interesting, like machine learning tools. Now, black box tools of machine learning are surprisingly powerful, and we saw people aiming to use them like to help with the particular things, tuning of model parameters, helping to tune the thermal properties. Nobody knows about them, but we know they are important. So some say dedicated use of these tools like machine learning tools, neural network, maybe with some help of physics, can be possible. And there is a lot of things in the RTTM-based leak detection, the processing and classification of the basic signal. That's a big topic, and the leak detection people are heavily investing in this. My time is over. I hope you are not over. Last but not least, we need some funny video. This is just to enjoy. This is a part of Prague City, and we as a feasibility study, we tend to show a propagation of biomethane from there is a wastewater processing plant that upgrades part of their biogas used internally for electricity cogeneration, heat and electricity. They need both, but part of that is now upgraded into biomethane and sent directly into city grid. They do carburation with propane to stay in some gray zone of the quality requirements. But we aim to do a simulation study, and those little magenta points, those were sampling points. and luckily we got a relatively nice comparison with samples. We didn't track calorific value because the gas is carbureted by propane, but we used ethane as a indicator because if you biomethane is methane plus nitrogen, CO2, oxygen in limited amounts, basically 95 plus % of methane. And if you carburate it, you get some propane and butanes, but you don't have a trace of ethane there. And traditional natural gas has a known share of ethane, so we use ethane as a marker who is who, and we were lucky to get things moving on say 130,000 nodes and edges of network, and handling a domestic consumer data to get things moving, and it worked. So it's a nice story that pipeline simulation is not a rocket science, but can do a nice enjoyable things. And I hope my time is over. I hope I was not too boring, not too long. Thank you for your attention, and any questions are very welcome. Thank you.